In this lecture, we will talk a little bit about the reaction Gibbs free energy and standard states. So far we have looked at predicting whether a process is spontaneous or not, depending on the Gibbs free energy. So now we have the tools necessary to determine the direction in which a biochemical reaction or a chemical reaction will proceed under a given set of conditions. And this last phrase is very important: under a given set of conditions. So we know that for any process at constant temperature and pressure, the value of delta G determines the uh, direction of spontaneity. Similarly, for any reaction at constant temperature and conditions, under standard conditions, I will define standard conditions a little bit later, but this is also described in pages 390 and 391 of Kurian very nicely. But what you have here on the left hand side is the standard reaction Gibbs free energy. R represents reaction. This symbol represents standard. Standard typically means a pressure of 1 bar and that the concentrations of the reactants and products are 1 molar. The temperature is usually 298 Kelvin, and these are the standard conditions. So if delta Rg standard is less than 0, the reaction will be spontaneous under those conditions, under standard conditions. To calculate the reaction standard Gibbs free energy, one can use the formula shown here, which says that the standard Gibbs free energy of a reaction is the difference between the standard Gibbs free energy of formation of the products multiplied by the reaction, multiplied by their coefficients in the reaction, summed over all the products, minus the sum over all the reactants, the coefficients for the reactants multiplied by the Gibbs free energy of formation of the reactants under standard conditions. So I will provide you with one example of calculation of the standard Gibbs free energy of formation. But to stress more about standard states, to compare the free energies of different reactions, we must first standardize the reaction conditions. And the standard conditions are typically 1 bar pressure and the temperature of 298 Kelvin. The standard state of a substance is its physical state at standard temperature and pressure. So for H2O, which is water, the standard state of pure water at 298 Kelvin and 1 bar is liquid water. This is the most stable state of pure water. Similarly, the most stable state of oxygen under these conditions is gas, and the most stable condition of iron under these conditions is solid. Note that the symbol of standard state differs slightly in Atkins and Kurian. We will stick with the symbols in Kurian. A standard concentration is typically 1 molar or 1 molal. For units, I strongly recommend that you go through section 3.2 in Atkins. We will revisit these units again and again during the entire course. So you should be very familiar with molarity, molalities, and concentrations. Okay, so the standard Gibbs free energy of formation of a substance is required to calculate the standard Gibbs free energy of a reaction. And the standard Gibbs free energy of formation of a molecule is defined as the standard free energy change accompanying the formation of 1 mole of the molecule from the constituent elements. So if you look at this reaction, this shows you the formation of solid glucose from solid carbon, gaseous hydrogen, and gaseous oxygen, because these are the standard states at 298 Kelvin and 1 bar. Now, by definition, and this is important, or by convention, the free energy of formation of an element, such as oxygen, hydrogen, and carbon, or iron, in the most stable form of that element under that condition, under standard conditions, is 0. So, for example, the standard free energy of formation of oxygen gas under standard conditions is 0. The same applies to hydrogen. The standard free energy of formation of carbon, solid carbon, will be also 0, but the standard free energy of formation of, for example, liquid hydrogen will not be 0 under standard conditions. A special case is given for protons. It is assumed that the standard free energy of formation of protons under in liquids is equal to 0. And this we will encounter in the next example. So here you have a reaction where half a mole of chlorine gas combines with half a mole of hydrogen gas to form hydrochloric acid, which under standard conditions is aqueous. So what you have on the right hand side is a proton and a chloride anion. If you look at the image on the right, it shows on the top that this is the actual reaction, but since HCl is aqueous, so HCl can be divided into proton and chloride. Based on the definition shown here, one can start writing the standard reaction Gibbs free energy. This is the standard Gibbs free energy of formation of hydrochloric acid. But this is equal to the Gibbs free energy of formation of a proton of the chloride anion. This is the product side. On the right hand side, you have the reactants. And you notice this half here, this is the reaction coefficient nu shown in this, or to be more accurate here, under reactants. So half the free energy of formation of hydrogen gas minus half the standard free energy of formation of chloride gas. By convention, the free energy of formation of an element in the most stable form is 0. So the last term falls off because it is the most stable form. The previous term also falls off. So these two terms are both 0 for the gases. I also said that the special case is given to protons. So this term is also 0. So essentially the standard Gibbs free energy of formation, excuse me, I just need to lower this here. The standard Gibbs free energy of formation of hydrochloric acid is simply the standard Gibbs free energy of formation of the chloride anion, and this is 131.23 kilojoules per mole, and this can be obtained from standard tables. So this is how you would calculate the standard free energy of formation of a compound, and from that you can calculate the standard Gibbs free energy of formation, standard Gibbs free energy of reactions, which you can then use to predict the spontaneity of a reaction under standard conditions. Let's take a more biological example. On the top here is a hydrolysis of ATP under aqueous conditions. ATP hydrolyzes with water to produce ADP and phosphate anions, inorganic phosphate. And it is known that the standard Gibbs free energy of ATP hydrolysis, delta Rg standard, is minus 28 kilojoules per mole, which means that the reaction should be spontaneous under these conditions. So a cell under standard conditions, in a cell, all the ATP should hydrolyze, given by the thermodynamic rules we have established. But this is not the case. So why is this? Even though the delta Rg standard is 0, less than 0, yet all the ATP in a cell does not hydrolyze under standard conditions. The answer is that there is an activation energy required to hydrolyze ATP. So this you must have seen before. If you have two reactants A and B and you need to go to C and D, sometimes there is an activation energy, although the overall free energy of C and D is lower than the free energy of A and B. So because of this activation energy, ATP does not spontaneously hydrolyze. So what should you do in order to reduce this activation energy? You have encountered this in biochemistry. You use an enzyme. So ATP hydrolysis in cellular systems is always coupled to an enzyme such as the sodium potassium ATPase or the F0 F1 ATPase. So are we at equilibrium? If we were at equilibrium, we would essentially die because delta G would be 0. But we are far away from equilibrium. We are not at equilibrium. Even our cellular membranes are not at equilibrium. The example of ATP here gives us some important information. The information that you can get from delta G is 1, whether the reaction will occur without external input of energy, and how far the reaction will go. However, delta G does not tell you the path that the reaction will take because delta G is a state function. It does not depend on the path. And secondly, it will not tell you about the speed of the reaction. This comes from kinetics, which Daniel will cover in another lecture. In the next part of this lecture, in the next video, we will combine the first and second laws of thermodynamics to derive the fundamental equation of chemical thermodynamics for single component systems. And we can conclude this video for now.